to get started? This will be the last talk in this presentation. I am making absolutely sure of it because not only I'm sure are you all tired of hearing me talk about this at this point, I am now tired of talking about this at this point. So I'm going to just briefly review what we got to last time, the tools that we have so far, and then I'm going to start with de Rham's theorem. I'm going to start with de Rham's theorem. The Eilenberg-Steenrod axioms that I haven't brought up so far, they will feature in the course of my argument. I will just name drop them, and then once I'm through with the main theorem, then I will go ahead and spend whatever time I have left over on the axioms that I didn't have time to cover last time. So hopefully we can finally get to this part of my talk now. So just briefly before we do that, I just want to write down singular cohomology because we defined that last time. We've been talking about de Rham cohomology this whole time. I'll write it down still again, just to make it clear to all of us, just in case anybody's forgotten anything about it. But then I'm going to launch right into the theorem. Okay, so we already know about I'm going to be talking about the de Rham cohomology for smooth manifolds, but we saw before that we can pass through another category called the smooth algebras to get to it. So we had a functor that took us from C infinity algebras. I'll call it a cochain functor here. And it took us to cochain complexes of real vector spaces. There was a bunch of other structure that it had, but that's the main thing that's going to be useful for the argument. It's got to be a cochain complex because that way we can go ahead and take its cohomology. And that was, in fact, what the de Rham cohomology functor was. We just applied the good old-fashioned cohomology functor that exists on any category of cochain complexes. We just applied that fellow to our Cartan de Rham functor that we got on C infinity algebras. We also had a functor that took us from the smooth manifolds, this being a contravariant functor now, that took us from the smooth manifolds to the C infinity algebras. And by abuse of notation, I will call the de Rham cohomology functor on this fellow by the same name. And you arrive at him simply by composing the one that we've already got with the functor that sends us from smooth manifolds to C infinity algebras. So by abuse of notation, that guy is also going to be HDR. Sorry, sue me. All right, so those are our de Rham cohomology functors. Those are all the things that we need to talk about today, and we saw their construction on the first presentation. We briefly talked about them last time as well. We also talked about singular cohomology, which was defined on arbitrary topological spaces, but for us, we're just going to be restricting to the case of smooth manifolds again. And it associated, again, manifolds now straight to cochain complexes of real vector spaces. And very briefly, how it did this is we constructed something called the singular chains on our smooth manifold. Those were continuous functions from the n simplex into our smooth manifold. Then we took formal sums of them, formal combinations. And then we, in order to get the cohomology, we just dualized this construction. We took the homomorphisms from these chain groups, these abelian chain groups, into the real numbers. That gave us the singular cochain complex with coefficients in R. So that's what we wound up with. We wound up with a sequence of these cochain complex guys, for some manifold with coefficients in R, just wound up being precisely the homomorphisms of abelian groups from the singular n chains that we defined last time. I used m into the real numbers. And where the boundary map, the co-boundary map on these fellows, comes from the boundary map on these guys, passing through duality, just by right pullback on these homomorphisms. So there we go. These are the functors that we start with, and to get singular cohomology, we just go ahead and compose this co-chain complex functor, again with the universal cohomology functor on co-chain complexes. Okay. There we go. That's our setup. Review over. We're all experts now on singular and de Rham cohomology. So what we're going to need is, because I'm trying to show you these things are isomorphic, I'm going to need a function from the de Rham cohomology group of any smooth manifold into its singular cohomology group, and then I'm going to need to show that it is both injective and surjective. So let's start by writing down what our map is supposed to be. So the first thing that we're going to need is the idea of integration of a form. And I should actually tell you more about what these things are. I don't have Sam's nice eraser here, but I do have a long sleeve shirt that I don't care very much about. Oh. Potentially. I have a shirt that I really don't care about, though, that might make a better eraser. Yeah, might make a better eraser. So we've got C, which is just going to be for us now a chain on, I'll use M consistently. It's just an n chain, so a formal sum with integer coefficients of n simplices. So I'll go ahead and use a different fellow here, A and sigma j, where sigma j are singular simplices, so continuous functions from the standard n simplex into our smooth manifold. So first things first, in order to pull off this integration that I'm about to talk about, I need these functions to be smooth instead of continuous. But for the generic definition of singular homology and cohomology, the functions are continuous. Now it turns out that adding the additional assumption that these functions are smooth actually comes at no cost due to something called the Whitney approximation theorem. In general, it says that any continuous function is actually homotopic to a smooth function. And homotopic chains will give you the exact same generators of cohomology. They will end up giving you exactly the same thing once you've passed to the level of cohomology. So I could go ahead and add, at no extra cost, the requirement that this fellow is smooth. And that will make what I'm about to write down actually legitimate. So now, integration of, and then I also was supposed to tell you what this form was. Omega is just going to be a form. So lambda is our form functor for smooth manifolds. It's just the composition of omega with C infinity. So this I want to be an n form on the same manifold. And that's it. That's all I need to, we all know what he does. I don't need to describe him any further. There's no proviso that I need to make like I had to make with singular homology. OK, now for the integration, what it actually looks like. It's going to be a bilinear pairing on chains on one side and forms on the other. And it will be given by sum over all these same coefficients. But now I'm going to, for every single one of these actual smooth singular simplices, I'm going to pull this form back, which is exactly what morphism this map sends sigma to. And that's going to give me the following, excuse me, it's going to give me integral over the n simplex, the standard n simplex of the pullback of that form there. So each one of these weird looking things is an integral over just a simplicial region of Euclidean space. Each one of these is just a smooth form on Euclidean space because this is a smooth function, and so pullbacks of smooth forms by smooth functions are smooth. So that's perfectly well defined. And it's clear also that this is going to be bilinear in both the chain argument and the form argument. OK? Well, because of that, we now have a map that associates forms to cochains. Because if I simply evaluate only the form argument, so defined, omega tilde acting on one of these n chains is simply equal to its value under the bilinear pairing. So we have an association, a map of forms, so lambda and omega, to smooth cochains. Again, it turns out that this is not a restriction, but it is worth mentioning. So M. But we'll notice, again, I want maps between the cohomology groups. What we've written down here are maps between the chain groups. So we need to show that, in fact, these maps extend, or descend, excuse me, to maps on the cohomology. So that's the first thing that we're going to show. We're going to demonstrate for ourselves. So I want so and what would it mean? It would mean that this map would commute with the differential. So let's go ahead and perform ourselves a quick calculation to convince ourselves that that does in fact work. So if I just go ahead and apply my definition, that means sticking these guys into my bilinear integration bracket. This is the boundary operator that we discussed for singular homology last time. Omega. We have an expression for such a thing. First, we apply what we know a generic cochain looks like and the bilinearity of this bracket. And also the linearity of our boundary operator. Okay. All right. Next, we apply the definition of our boundary operator, which, if we recall, it just sums up, together with a sign, the inclusions of the faces of the standard singular M simplex into the standard singular M, the standard M simplex composed with this map. So that's a lot of words. Let me go ahead and write down symbols. J, and now sum I is equal to 1 up to n plus 1. We've got an alternating sign that changes with the choice of endpoint that we pick, encoding the orientation of our figure. And then we have, so this guy becomes now sigma j composed with the ith inclusion, so n, I, I shouldn't use I, because now I'm already using him for something else. I'll use k. K, omega. Okay, there we go. Now, this is still a singular simplex. It's now going from an n-1 simplex instead of an n simplex. But that's fine because I should have also mentioned, big goof that I did here. If n is if C is an n simplex, then the boundary operator takes me down in dimension, so omega actually has to be n-1 for all of this that I'm writing down. Apologies for my mistake there. This part is still true with the indexes matching. Okay. Sigma j. Nope, he is the correct degree. He's supposed to be degree n. It's the form that was too high degree. Okay, so the boundary of sigma j, first of all, we understand that the singular n simplex has a boundary. He has all of his faces. The boundary operator on sigma j sends, or for any singular simplex sigma, always sends to just a sum, so another cochain. So k again, just to match my other notation. Always sends us to a sum of other singular simplices, and the way that we arrive at those singular simplices is by including the boundary of this fellow's domain and composing him with that inclusion. okay? And where these signs out front are meant to take into account the various orientations of the different sides of the simplex. So boundary for a set, we understand what that means from topology, but boundary for one of these chains, it means this linear operator. It does, in fact, still come geometrically from the boundary of some set, but it is itself a linear operator on a group, or a homomorphism on a group. Z-linear, if you like, because these are all abelian. It sends things from, and I can see now where the confusion is coming from. It sends us from singular n chains on our space X to singular n minus 1 chains. And the reason why it does that is because what it means to be an n chain is that you're a formal combination of maps from the n simplex into our space. But by composing with these inclusion maps, I have now reduced the domain of this fellow from the n simplex to the n minus 1 simplex. Each one of these boundary maps, which is also worth defining here, they yes. Yeah, it's still defined. It will just be over the lower dimensional simplices. It's still a simplex now for the 1 degree lower, but this formula, this definition here, didn't depend on our choice of n. We could have chosen n to be any dimension. As long as we're pulling back a form of the same dimension by a simplex of the same dimension, this integral will be well defined. Good question. Thank you, though. Okay. All right. Let's back to this fellow. So now at this point, we can go ahead and insert in our definition of this bilinear bracket, which is just an integration. And that will allow us to bring Stokes' theorem into the mix, because it's what's actually powering this result, the fact that this tilde actually does, in fact, introduce a chain map, a cochain map even. Okay, so and now these will be integrating, again, as was just brought up, these will no longer be integrating over the n simplex, because each one of these fellows is an n minus 1 simplex. So it'll be integrating over the n minus 1 simplex, which is very important for this to actually work out the way it's supposed to. So now, again, by our definition, we look at what's showing up here. We go ahead and pull back our form by this entire map here. So J pose I and K, pullback of our form omega. All right. Well, the next step, the process of doing pullbacks, it's the morphism part of this functor, of the Cartan-de Rham functor on smooth manifolds. It's contravariant. It doesn't preserve the order of compositions, it swaps them. So this is the same thing as, I'm going to do a little bit of proof by eraser, hopefully everybody will forgive me. This is the same as the pullback of the inclusion first, acting on the pullback of sigma j on this fellow. Okay? Now, integrating over all of these different boundary faces together with these different signs out here is the same as integrating over the entire boundary of delta n, because these signs are exactly encoding the different orientations of the different faces. These inclusions are including us into the different faces. So we can go ahead and replace this with J. So again, this is now going to be just the inclusion of, I'll go ahead and define this map before I write them down, the inclusion of the boundary of the n simplex back into itself. So that's what I'm going to end up replacing all of this stuff with here. And in fact, I'm also going to end up getting rid of this sum, so I don't need him either. So that just becomes integral over delta n minus 1. Oh, delta, it should be delta n actually. But no. This is including the boundary of the nth fellow into himself. This one should be a lower dimensional. It's made out of n minus 1 simplices, just like we started with over there, and it's winding up the boundary of an n simplex. So this now acting on, again, same thing. J omega. All right, but now we have classical Stokes' theorem, because I'm including into the boundary and I'm integrating over that boundary. Stokes says that I can go ahead and replace this, and because this omega is a form on my entire space, otherwise I'd have to mention the idea of extension. But because it is a form on my entire space, I can go ahead and replace this integral over the boundary with an integral over the n simplex again, but now I've replaced the inclusion with a differential. I have to increase the degree of my form, because otherwise it's not going to be the correct degree to integrate over an n manifold. It will be an n minus 1 form. Okay. N, and then now our differential of, and everything else stays the same. Okay, from here we use the fact that these pullbacks are cochain maps, so differentials commute with them. So I can go ahead and pull him right through. J, and this fellow just goes right into there. But now, if we look at what we've written down here, this is exactly the definition of integration over a chain, but with our form being d omega instead, which is exactly what we sought to prove. D omega, which is d omega tilde acting on C. So the boundary operator, the co-boundary operator acting on omega, which is the same as just composing him on the right with the boundary operator, is the same thing as taking the differential of omega and then putting him through our map tilde. So this is in fact a cochain map, as it's supposed to be, and hence this fellow descends to cohomology. He gives us some homomorphism between the cohomology groups of de Rham cohomology and singular cohomology with real coefficients. We now have to just show that that is in fact an isomorphism, and that is going to be the role of all of these crazy axioms that I've been trying to hawk to you guys over the past couple of weeks. Okay, I'm going to start erasing this stuff. Okay. So we want to show that the version of this now on de Rham of our manifold to singular cohomology of our manifold with real coefficients. We want to show that that's an isomorphism. But because we know that both of these cohomology theories satisfy the dimension axiom, we know one set of situations in which it's certainly going to be an isomorphism, namely, if M consists of a single point, well, by the dimension axiom, the de Rham cohomology only exists in 0th order and it's equal to R. Every single other higher order, it's 0. We saw that at the end of last presentation. So the same is true of singular cohomology. I didn't prove that, but it is true. And that tells you that at least for points, which not very interesting as spaces, but we all have to start somewhere. For points, this map is in fact an isomorphism. So tilde is an isomorphism. Actually, you know what? I should, the induced map of tilde right? Because tilde is between the co-chain complexes. The induced map, the one between cohomologies, is an isomorphism. Okay, but if all we did was study points, we would have very boring jobs. So there are other spaces that are more complicated from points, but which this isomorphism easily extends to. So if M is contractible, which means it's homotopy equivalent to a point, by the homotopy axiom, which I haven't proven for you yet for de Rham cohomology, but which is true of both singular cohomology with real coefficients and de Rham cohomology, homotopy axiom implies that any two spaces with the same homotopy type have the same de Rham cohomology and the same singular cohomology. And if a space is contractible, then it's homotopically equivalent to a point. So if it's homotopically equivalent to a point, the dimension axiom tells us we know exactly what its cohomology is. And so in this case, the induced map is also an isomorphism. And hopefully you now see what the strategy is going to be here. I'm going to build all of the smooth manifolds out of contractible pieces. Or I'm going to build some smooth manifolds out of contractible pieces, and then I'm going to show you can build all smooth manifolds out of those smooth manifolds, and that will give me the end result. And what's nice about this theorem, this is not how de Rham first proved this theorem very many years ago, but the theorem of uniqueness of cohomology theories satisfying the Eilenberg-Steenrod axioms proceeds exactly along this way. The proof that I give you here can be easily generalized to any other category on which you have cohomology theories satisfying the Eilenberg-Steenrod axioms. Okay. I have a red marker. That may be better. It may be worse. We'll see. Okay. So there we go. As long as we're only interested in studying contractible smooth manifolds, de Rham's theorem's already proved, you guys can go home. Okay, but not yet, please, hopefully. All right. Now, we also have that. And I haven't, again, this is not one that I got to last time, but we have something called additivity, or in general, decomposability. For us, it's that if I have the homology of a disjoint union of smooth manifolds, obviously countable because you can't take more than countable disjoint unions of smooth manifolds and still get a smooth manifold. But if you have a countable union of smooth manifolds, then it turns out that the cohomology is simply the product of all of the component cohomologies. So you have a nice way of learning the cohomology of spaces that you can decompose into pieces. Let's use a different index here. Okay. So that's important because now, in light of what we've already shown, if M is a disjoint union of contractible spaces, then our theorem easily again extends to this case. Contractible manifolds. Then we have that the induced map is certainly an isomorphism. Okay. So far, the first couple of steps of this proof have not been very interesting. I've just been going along and saying two things are isomorphic. Just using the properties alone, there hasn't been any actual work to do. But now at these next couple of steps, where I show that you can, in fact, make smooth manifolds out of other smooth manifolds, there is going to be a little bit of work. We're going to go through a short tour of some facts in differential geometry. So first off, I would like to now start moving on to extending this result to compact manifolds with boundary. Adding boundary to the situation doesn't change anything at all. All of the same definitions pass through, so I'm not going to go ahead and redefine anything for that case. But the reason why I care about compact manifolds with boundary is because you can exhaust any smooth manifold using a countable collection, an increasing countable collection of compact manifolds with boundary. So if I can prove the result for compact manifolds with boundary, and I know something called the Milnor exact sequence, then I can go ahead and prove the case for any smooth manifold. So I'm not going to prove any homological algebra for you today. You're all just going to have to believe me about it. OK. So then, how are we going to get to apply any of our axioms to compact manifolds? Well, the one that I'm trying to get to, the one that I would like to use, is something called the Mayer-Vietoris sequence, which isn't actually one of the axioms, but it follows from two of the axioms called excision and exactness. So I'll go ahead and write that out, what it says. But it's an incredibly useful fact that makes calculating cohomologies out of pieces of spaces much, much simpler. Okay. Okay. So this sequence, which is a long exact sequence, it goes on, it starts at 0, and then hits the 0th order cohomology, and then just continues to increase. No. We've tried to figure out how to get this thing to do better, but it's... We literally can't even keep the lights on around here. Anyway, OK.
So, you're trying to show this as one, right?
Yes.
And you're going to use this long exact sequence to do that?
Yes, I am. Exactly. And what's going to happen is I'm just going to break off a particular chunk of this sequence. I'm going to take, this is the guy, this is X right now. I have him written as a union of two open subsets. And I'm going to have this chunk to one side and that chunk to another side. And if I am able to cover my compact space with contractible open sets whose intersection is contractible, then we already know by the theorems that we've proven so far that these two guys have to be isomorphic between singular cohomology and de Rham cohomology. Both of these guys on either side. And then we have access to something from homological algebra called the 5 lemma. If we have a ladder of exact sequences where these fellows are isomorphisms over here, then this map, whatever it is, has to also be an isomorphism. So, but then the problem comes, OK, is every compact manifold the union of two contractible open sets with contractible intersection? No, that's not true. As an example, consider the sphere, right? There is no pair of two open sets. So that guy right there. There's no pair of two open sets that you can cover this thing with such that their intersection is contractible. This is just a generic choice, but trust me, you can't do better than this. If I had this open set right here and this open set right here, it sure would cover my sphere, but its intersection has non-trivial homology. It certainly can't be contractible. OK, so how do we deal with that? Well, it turns out that we can always shrink the elements of our cover and add some more elements in order to get out of this situation. Namely, if I just went ahead and cut out, if I complemented this open set with the closure of this open set, and same thing vice versa, so I missed this middle strip, well, then I could just cover that middle strip with a bunch of disks, each of which is overlap, is simply, obviously, a contractible set. And you'll just have to believe me that generically you can do this on a compact manifold. You can, in fact, always shrink an initial open covering by contractible sets and end up filling in any of the points that you missed by adding more disks that are sufficiently small so that their intersections are also contractible. This is always possible. This can always be done. Proving it would... I'll give you a sketch of the proof. I've already given you a sketch of one part of the proof. Once you've got an open cover of contractible open sets, then you can shrink it sufficiently in order to get it to be one that you want. But how do you get an open cover by contractible open sets? Well, for any smooth manifold, there exists a Riemannian metric on that smooth manifold. And for any one of these Riemannian metrics, you can always find around any single point a geodesically convex open set. So you just take the distance function that's given to you by that Riemannian metric, and you take a metric ball around your point of sufficiently small radius. And that will always give you something that's geodesically convex. So you can always make a contractible open set. And in fact, because every single point will have one of these disks, and we're on a compact manifold, at least for the case, we can in fact come up with a finite collection of contractible open sets that covers our space. Okay. And that will allow us to use this fellow and an inductive argument to prove the case for all compact manifolds with boundary. So let's go ahead and briefly outline that. For compact manifolds, you can always find a finite open cover whose every element is a contractible open set, and such that all intersections between elements are contractible open sets. What's known as, exactly, pairwise, in fact, for higher order intersections, you can take any order of intersection, it will always also be contractible. It's what's known in the biz as a good cover. All right. So first step, we're going to do the base step of our induction. I'm going to show you that this strategy of using the Mayer-Vittor sequence does in fact work if we can show that our compact manifold is the union of two contractible open sets with a contractible intersection. So I'll just go ahead and write. It is just going to be me waving my hands and saying the phi lemma, though. So that's all that's going to happen. But it is instructive to see it in action. So we've got this fellow, so I need those guys to the right of, or this fellow, so I need those guys to the right of him. So J, U, direct sum, V, off to the intersection, to the guy we care about, who I'll write as M now, but M is just the union of U and V. And then once we, excuse me, I missed this, but once we get to this fellow, we jump up in degree. So this should be J plus 1, and all of the following guys will be J plus 1 as well. Okay. And these sequences are exact, both for okay, so we get the same thing for singular cohomology down here. And we've got the induced tilde maps that go from de Rham cohomology down to singular cohomology. Okay, so as I mentioned before, if I have a pair of exact sequences and a ladder of homomorphisms between them such that all of these different squares commute, if these four maps on the very outside are isomorphisms, then the map on the inside is an isomorphism. But that's exactly saying that if M is a union of two contractible open sets, U and V, with a contractible intersection, then the two de Rham and singular cohomology is isomorphic. And again, we know that these fellows are isomorphisms because we know that these guys are contractible, and hence we know exactly what their cohomology is, and it has to agree with their singular choice. And same thing for the intersections. Again, contractible, we know exactly what it is. Special case that we've proven so far covers that. Okay. I have a very scattered, I never took homological algebra formally, so I have a very scattered view of all these various theorems. I've only ever seen and used them in very particular contexts, so I might be lacking the general picture that I probably ought to be presenting it in, but since I'm not going to talk about it more, I figured I'd just name drop it and move on. Okay, so now how can we bootstrap this on up, right? This is our base case for this inductive argument. If we have two components of our finite cover, then the conclusion holds. So now let's suppose that we had K. So M is equal to a union of K open sets, where these open sets have been chosen to be a good cover, just as before, because we know such a thing exists. Okay, well then it can be written in the following way, and we also assume that the fact is true for K minus 1 and everything beneath it. Well, then this can clearly be written as UK union all of the lower order fellows. Oh, that's why that didn't make any sense. Okay? So this is now a union of two things. It's in the situation where I can apply Mayer-Vietoris. But if we go ahead and look at what the pieces of Mayer-Vietoris are for this given decomposition into unions, I'm going to need to know the cohomology on UK, but that's fine. He's a contractible open set. I know what it is. I'm going to need to know the cohomology on the union of these K minus 1 open sets. That's my inductive hypothesis working. I'm going to need to know the cohomology on their intersection. That comes from the fact that this is a good cover, and so the intersection of this with this has to be a contractible open set. Okay. So exactly the same way that, using the exact same Mayer-Vietoris that I wrote up here, we get exactly the isomorphism now occurring at the level of a cover with K elements, and since that's one more than K minus 1, we're done. It goes on for all orders. All right. And that means that so far, what we've learned is that if M is, in addition to knowing that it's a disjoint, if it's a disjoint union of contractible manifolds, our induced map is an isomorphism. If M is compact with boundary, then our map is, again, an isomorphism. Okay, we're almost there. We've got the case of compact manifolds with boundary, then is an isomorphism. Now all that's left is to introduce one more fact from differential geometry / differential topology about smooth manifolds and their relationship with compact manifolds, and then again to wave my hands and state some more homological algebra results. Okay. So I mentioned it already, but one can exhaust a smooth manifold, an arbitrary smooth manifold, by a countable collection of compact smooth manifolds with boundary. And by that I mean it can be written as an increasing union of this countable sequence of compact manifolds with boundary. But it's not obvious why that's true, so I'll again briefly sketch a proof of why that is true. And then I'll go ahead and wave my hands about my last homological algebra result, and then maybe I'll have enough time to actually state the rest of the axioms in full, though we will have seen their highlights throughout this argument. Okay. So what we're trying to show, M is equal to a union of compact submanifolds. For any smooth manifold, M, there exist Morse functions, which are functions that have non-degenerate, we say, critical points. A critical point is any point on your domain where the function's differential is equal to 0. So critical point, very similar to the definition that we're used to from elementary calculus. A Morse function has the property that his Hessian matrix, his second derivative matrix, at that point is a non-degenerate matrix. It's not, it will have some eigenvalue that is not 0. And it turns out that you can, through a change of coordinates, put it into a particular form where, in fact, its eigenvalues are all 1 or -1. and that gives you something called the index of the Morse function. For if you go off and study Morse theory, we won't be doing that today, but that's where this fellow actually comes from. That's why generally people care about him. That's not why we care about him today, though. We care about him today because we know that his critical point set is isolated. And so in particular, we know that he has a lot of regular values in his codomain, in his range. So I can go ahead and define the following collection of sets. So F inverse of minus A, and I'll go ahead and choose N and N. Choose this to be K sub N. So F maps into the real numbers. I'm just taking an increasing collection of intervals of the real numbers, increasing in both directions. And the preimage of this fellow is going to be compact, because another fact about Morse functions is that we can choose proper ones. So this will be proper, meaning the preimage of a compact set is compact. So that's what's giving us compactness. That this thing is actually going to be a smooth manifold will follow from the regularity of our function at these numbers n. So perhaps I could actually choose a sequence instead, because it's not guaranteed. It's not guaranteed that f is going to be regular at every single integer value, at every single natural number, but there will be a sequence of numbers, of real numbers, going off to infinity on which f is regular. And so I can take any such sequence, and any such sequence will define an exhaustion. So I can go ahead and build out of an ever-increasing piece of compact submanifolds any smooth manifold. And that, together with a result called Milnor's exact sequence, which gives you a relationship between what are called inverse systems of chain complexes, which this will give us once we pass through to the cochain complex. We get an inverse system of cochain complexes, and then the following very scary sequence is short exact. So lim backwards of, now I have 1 applied to each k, and that guy goes forward to, and this, I'll mention him a second ago, that I didn't mismark here. This is not the inverse limit. This is something slightly different. Excuse me, this one is on the inside. Okay, and then outside. Okay. So this short exact sequence, I claim, can go ahead and give you now the cohomology for the rest of the smooth manifolds. I'm not going to go ahead and show you how. I'm just going to tell you, and I'm going to hit you with the spell that makes you believe me. But the one word I would like to say about this fellow over here, these are inverse limits in the way that you would be familiar with them from category theory, if you're familiar with it. But this is not the inverse limit. This is actually the first derived functor of the inverse limit, where derived functors come from Grothendieck's perspective on cohomology. His general way of constructing a cohomology theory was to take a left exact functor and construct the right derived functors from it. And those higher derived functors are exactly a cohomology theory associated to whatever your original functor was, where in the 0th degree it is exactly the functor you started with. As I've said functor a whole lot, so now I'm done doing that. And again, that's where this comes from. That's one of the reasons also why I'm not going to be showing you any explicit calculations with it, because it would take me forever, and I'm already technically out of time. But thank you all for sitting here just a little bit longer for me. Okay. So there we are. With this and the exhaustion of a smooth manifold by a countable collection of compact manifolds, and our previous results, the fact that we know that it holds for compact manifolds, we now have access to de Rham's theorem for all smooth manifolds. And this method of proving de Rham's theorem, well, again, not historical. This is very different from how it would have been done originally. It is exactly the method that you would then go to use to prove the Eilenberg-Steenrod uniqueness theorem for any cohomology theory that satisfied the Eilenberg-Steenrod axioms. You need some method of generating all of your objects out of the constructions that show up in the axioms, things like taking disjoint unions. You need to be able to build them up all out of your basic objects. Those are the things that are equivalent, in our case homotopy equivalent, to your simple space, in our case a point. So you have some notion of equivalence, some notion of basic simple spaces that are equivalent to the most easy to calculate things in your space, some way of building up all of the other objects in your category out of these most simple objects. And that gives for you a big, long machine that tells you that there is only one way to define cohomology on such objects that has all of these properties. OK. I actually kind of feel like I'm happy leaving it there. I could sit down and write down all of the other axioms for you, but I wouldn't have a chance to prove any of them because it would take me much longer than the time that I have left. If any of you are curious about the other axioms and their content and maybe what they say differently in homology or cohomology, feel free to come and ask me about it. But as a treat, I will release you all 20 minutes early. Thank you for coming to all 3 of my talks. This was a bear, so I really appreciate it.